So now that we know what an inverse function is, just the function that switches the input and the output, let's figure out what the derivative of an inverse function is. So, to figure out what the derivative of an inverse function is, we're going to start with kind of the main definition of the inverse function. But first, let's let g equal f inverse, because g is just a much nicer thing to work with than that notation right there. That means that f composed of g of x gives you x, right? That's the definition of the inverse function. Next, we differentiate both sides. So differentiate the left side and differentiate the right side, which maintains equality as long as you differentiate both sides. Now, the left side is the chain rule. So the derivative of f of g of x is f prime g of x times g prime. And x just differentiates to 1, right? Because the slope of the line y equals x is 1. Now what we want is g prime. Because our goal here is to find the derivative of an inverse function, and g is our inverse function. So we want g prime. So all we do to solve for g prime is just divide by the f prime g of x. And if you want to use that f inverse notation, this means, all right, over here, the derivative of f inverse is 1 over f prime f inverse of x, which is kind of a mess. It's hard to memorize that. It's also hard, by the way, to do this a different way, because you might think that if you want to find the derivative of the inverse function, you could just find the inverse function, right? Like, for example, if your function was like x cubed and you want to find the derivative of the inverse, why mess around with this? Just find the inverse function, which is x to the 1/3. The problem is that even though it was easy to find this inverse function, finding inverses is insanely difficult in like many cases. Even if the inverse function exists, the methods to find the inverse function might be well beyond the scope of this class. Just a ton of algebra, a mess of algebra, stuff that we don't want to do. So instead, this is actually the shortcut. Instead of doing the humongous mess of algebra to find the inverse function, if it's even possible to find it, you just use the fact that the derivative of the inverse is 1 over f prime of the inverse of x. However, there's a better way to do this. Like this is possible to do. And by the way, I have a hard time memorizing that. Like, I don't have that memorized. Instead, if I absolutely had to use this for an exam or something, I would just do this derivation every single time. I would just start with this, knowing that I want the derivative of g of x, differentiate both sides, solve for g prime. That is the derivative of the inverse function. It's much easier to do this than it is for me to memorize that. But a lot of times you don't have to memorize anything. For example, here's kind of the more common sense way to look at this. If I use the graph that I had on the previous clip, or something just like it, we had a function and its inverse graphed. We'll say like there's the function, and then here's the graph of the inverse, which is symmetric about the line y equals x. And the thing to remember is that all the inverse function does is switch the xy coordinates. So for example, those 2 points correspond because b comma a is the result of the inverse switching the input and output a comma b. And so the slopes, right? Let's say, for example, that this slope right there was like 2/3, or 2/5, since I wrote that down for some reason. Well, this slope of the inverse function would be 5/2. which makes sense because all the inverse does is switch the x and the y. And slope is the change in y over the change in x. So when you flip x and y, the slope also gets flipped over. This is pretty much saying that. It's saying the slope of the inverse function is the reciprocal of the slope of the function at the corresponding point. Just go to the corresponding point, find the slope there, and then flip it over, which is what we did here. We go to find the slope at b comma a, we go to the corresponding point, find its slope, and then flip it over, because the inverse just switches x and y, so the slope is just flipped over. To see that kind of in a more specific example, let's say you have some function and you knew that f prime of 4 equaled 6, and that this graph had the point 4 comma 3. That means that the corresponding point on f inverse is 3 comma 4, since f inverse just switches the x and the y. And the slope at this point, f inverse prime of 3, is 1 over 6. Because the x and the y get flipped, and switching the x and the y flips over your slope. As an example of how you might encounter a question like this, let's say we knew that the tangent line to y equals f of x at x equals 2 is y equals 7 plus 8 times x minus 2. And you want to find the tangent line, or you want to find an equation of the tangent line to the inverse function at x equals 7. Right, so press pause and give this question a try. You know the tangent line to f at x equals 2. You want to find the tangent line to f inverse at x equals 7. So press pause, and when you're ready for the solution, press play. So there's not much to do here in terms of math. Most of it kind of happens in your head logically. We can see from the equation of the tangent line that the point is 2 comma 7. So on the graph of f of x, we have the point 2 comma 7, and the slope of that point is is 8. Well, this means that on f inverse's graph, the corresponding point is 7 comma 2. This is the point that you get by switching those inputs and outputs. And the slope at that point will be the reciprocal of the slope at the corresponding point, because you switch x and y, which means slope gets flipped over. And so our answer for the inverse function is y equals the y value of the inverse function plus the slope of the inverse function times x minus 7. So the inverse function switches the x and the y and flips the slope over.